Hello, everybody. I'm John McLoone, and I have worked for Wolfram for a long time and lead the technical services group in Europe. And as we're imminently about to launch Wolfram language version 12.3 with new versions of Wolfram Desktop and Mathematica, I've been given permission to share a bit of what I know about what's coming up. So what I wanted to do today was to spend most of the next hour walking you through a slightly personal perspective on what I think is interesting out of the new release. It's been 5 months since the last release, and so there's been quite a lot happening, so I'm not going to be able to show you everything. I'm going to hopefully put together a few examples here to give you some flavor of what some of the new functionality will do. So to preserve a bit of bandwidth here, I'm going to share my screen and take myself off camera. So let's see, share the correct screen here. There we go. And let's take myself off camera here. Great. Okay, so hopefully you're seeing my notebook, and let's get started. But before I jump into the things that are new, it's worth just setting the scene a little bit. And from my point of view, what we're trying to do with the whole Wolfram technology stack is unified computation. So we're trying to make it so that it's not just a bunch of features, but it's a unified whole. So while I'm actually going to be showing a bunch of features today, actually a lot of the thinking behind what goes on isn't just about clocking up lots of new functions. And while there is a lot, 115 completely new function names in this release, although that's a terrible metric because what we really want is functionality, not functions. And in fact, there are several functions in this release that have huge amounts of functionality behind them, but they're just a single function name. But a lot of what we're trying to do is to build out this idea that it's all unified. So you'll see as we go through that a lot of the changes here are kind of infrastructure improvements that allow core functionality to work better, functionality to join up better. And we've tried to touch on lots of different domains. So it's very appealing to try and say this is the X release, which has some top most exciting feature. That's not really the way I'm going to present it here, because I think the key here is that we're doing everything at once and everything's getting better. Having said that, I've got to pick an order. So I thought I would start with perhaps some of the most widely influential aspects of the 12.3 release, which is affecting performance. But I'm going to do this slightly backwards because I'm going to drill into something which is really a kind of narrower power user functionality. The compiler is a big project that's going on at the moment to make Wolfram language compilable in LLVM so it can run really fast and take advantage of optimizations based on knowing what kind of data you're getting. So there's been some big improvements to this long-term project. The main significant thing is that up until now, the LLVM compiler has been about compiling a function. You can say, here's a piece of code for a function, and I know that the values are reals, and therefore you can make it run faster. We now have tools for compiling whole collections of functionality so that the functions know about each other during the optimization stage. And so for making larger scale packages run fast, that's a really big improvement. And there's some detailed stuff like support for further data types that weren't previously supported. Now, the rest of this slide is sort of downstream from that. Part of the compiler approach is to deal with optimized data structures. Now, Wolfram language is really flexible, and you can do anything in Wolfram language. You can make all kinds of specialized data structures and customized algorithms assuming that data structure. But that work is left to you. And if you use just the general functions, then the price you pay for all of that ease of use and quick coding is sometimes slower performance. So we now have, I think, about 25 of these data structures. The three that are being added here are byte trie or byte tree, depending on your pronunciation, immutable vector and KD tree. So byte trees are great for sort of auto completion type things in sequences, KD tree for nearest neighbor type operations. I'm going to show you an example here from the simplest, which is immutable vector, which is the most like the built-in list. So here's an example, and I'll just rerun this now live, of a not very good bit of code, because if you've read my blog on fast coding, appending to a list repeatedly is not a great way of accumulating data. So it takes 4 seconds. But using this new data structure, immutable vector, that behaves just like the list, but is now optimized. It can do fewer things, but what it does, it can now do much, much faster by very customized representation and customized algorithms for appending and replacing and so on. So you can see here we're getting, what, 40, 50 times faster by changing this to the data structure. So those things are fairly easy to use without having to know anything about the compiler. You can just pick up the data structure and use it. But then that all sort of flows into more of the Wolfram language. So what we're starting to do for the first time with this compiler technology is to point the compiler back at the Wolfram language itself. So in this release, a whole collection of functions have just had, okay, it's a bit more work than I'm going to make it sound, but basically we've wrapped function compile around the code that defines these functions. So even though they're written in top-level Wolfram code, they're now running as fast as if they were written in C code. So we're getting things like around, which is the experimental data structure for errors, experimental error propagation is now about 100 times faster than it was. Rasterize important for any kind of video or kind of web applications, 3 times faster. And then if you look at some of the different domains like signal processing, these sort of wave generators are 10 times faster. And this is all part of now a long-term strategy of the compiler, is to point the compiler back at the Wolfram language and compile more of the code that we've been writing over the years and just make it run faster. So this is really the one that will be most influential out of this slide, because you don't have to do anything. If you're using code that uses around or rasterize or distance functions or geometric transforms, it will just run faster without you having to do anything. Not affecting everyone, but Windows, of course, is the major platform. We have now direct write rendering in the front end. So that means if you're doing 3D graphics, particularly things like rotating 3D graphics, then it uses the direct write engine. And the real advantage of that is that it'll make use of GPU. So if you've got a nice computer with lots of GPU power, rendering will get much, much faster as well. Again, without you having to do anything to make that happen. Now, the next most kind of common point of contact, other than the language, is the notebooks. And there's several small but important things happening to the Wolfram notebook in this release. And I break them into 2 categories. Things for making coding easier. So you're writing Wolfram language in code, so in a notebook, the most typical use of notebooks. And we want to make that just easier to do and do right. But notebooks are a really powerful and flexible way of bringing together different kinds of workflow. And so we're doing more to make it possible to use notebooks for things other than just directly writing code and debugging code. So in the code easier area, we've got things like code analysis and new typing tools and iconization. They're a bit hard to explain, so I'm going to show them is going to be the easiest thing here. So let's switch to a notebook here that I've got behind the scenes. So not in presentation mode now, a typical working notebook, and I've got some code in it and some other stuff that I'll show you in a minute. Now, for those of you who are really top-notch Wolfram language coders, you'll see this code is not very good, but at a glance, it's not always obvious, and when it's complicated code, it's definitely not obvious. So we now have these 2 new menu items: Analyze Notebook, Analyze Cells. And I click Analyze Notebook, and it's going to do a little bit of thinking, and now it's going to tell me what's wrong with my code. So it's spotted here that this module variable x2 wasn't used, so maybe that's a mistake. It's spotted in this other piece of code another unused thing. In this case, the parameter for the function was never used on the right-hand side, but also it's spotted the missing semicolon, which means implied multiplication. And some of these things will come with auto correction. So if I click on this, I can see, well, there's 3 sensible things I might do here. Maybe I missed out a semicolon. I can click on that and fix the code. Or I can say, no, this was a good code, discard the edits and get rid of the suggestions and go back to where we were. So it's very easy to write bad code, of course, simply by carelessness or mistyping. And because Wolfram language is quite flexible, sometimes it propagates that badness deeper into the code. So now it's going to be a lot easier to do this static analysis at the top level. Now, in terms of alternate uses, we've got a new object that is at the beginning of its development process, but is already useful, and it's this question object. And the idea is that for those of you particularly using notebooks for education, you can now set up little quizzes in notebooks in a very simple way. I click that and it tells me I was wrong, that in fact perhaps the answer was 755. Yeah, that's how many home runs we got. And the idea is to make these really easy to create. So there is a question object which has a question, and this assessment function which landed in version 12.2, which allows you to describe in a rich way what is a right and wrong answer to the question. Now, this is going to build out more in future versions, but already for simple kind of in-notebook quick quizzes is already quite useful. Another thing we're trying to do with notebooks is make them a hub for your technical working, not just because we want to make Wolfram language a hub, but there are other things that you do while you're working, and we want to make the notebook a place where it can all happen. So for a while, we've had the ability to put code from different languages into the notebook alongside the Wolfram language code, and we're adding 3 more cases of that here. So You can see if I pick the choices here that we've already support things like Python and R and Julia and so on. But now we're adding shell scripts to the notebook. So within the notebook, I can type some, in this case, Unix commands as say, list the files in the long form for the current working directory. I can write Java directly into the notebook. So here's initialize a vector of 20 integers. And that's coming back into the notebook in a reusable Wolfram language form. So that translation as it's delivered gets done so that I can compute with this directly in Wolfram language. So I can dip in and out of different languages into databases. And the last new one here is, if I evaluate this is running in Octave, which is a kind of open source sort of MATLAB clone. So I can write effectively simple MATLAB code in the notebook here. Unfortunately, Octave isn't quite as accurate as we are. If we compare that to the true answer, then you see they've only got the first 10 decimal places right. But you know, maybe that's still useful to me to be able to switch to the other systems. And there's going to be more of those, of course, in future. The last one is really just a nice little bit of usability. Here's a typical problem about notebooks being reusable. You want to be able to do computations, and while we're running the computations, all very at my fingertips. I can do lots of stuff. But what happens if I save this notebook? This is a big piece of data, 10 to the 7 numbers potentially. So what we do by default is data not in notebook. So this is just effectively a picture. And you can see that if I copy that down and say, you know, what's the total of that object, it'll say, well, actually, the object doesn't contain the data. It's just the summary. Now, for a while, you've been able to store the data in the notebook by clicking on it. But that makes your notebooks really big. So now we've got 2 new options that just automate the process of storing the data and linking it back in, store in local and store in cloud object. So if I click on store in local object, it's now saved that to disk, but it's linked it back into the object here. So if I paste that back into here, we can now see I can compute with that. And if I open the notebook in future, I can compute with it. Even though the data is not in the notebook, it knows where to get it from to make that the contents of the notebook reusable. So small feature, but you know, really kind of improves that ease of use workflow. Let me show one more notebook thing here. Let's do new programmatic notebook, form authoring notebook. We've had form notebooks for a while. We use them for things like the function repository submission, where you can fill in a notebook as if it's a prompt for an interface for prompting you for inputs. We've now got a much more point-and-click way of generating those things. So I can use it like a notebook. I can put a title in, but I can insert content in here like a form element. And maybe we're going to have some radio buttons in here. And this itself is a form that now prompts me for the information that I might need. I'm just going to accept those, and I can preview what it'll look like. I can decide what the form will do when I click on it. And then I can generate the form when I'm done. I didn't actually tell it what I want it to do, so I'm going to tell it now, just create a document. But typically what you're going to want to do is to do something like submit it to a data bin so you can accumulate the data. But here I'll just create the document. And what you end up with is the generated version of this document that you pass on to your users or you cloud deploy, and they give their answers and click submit. And in this case, I told it just show me the data object that is generated, but that's the thing you would put into a data bin or run a program against or send an email against or whatever you want to do to process the information. All right, let me close that and go back to the talk. Right, let's go to computation now. And I thought we might as well start with the eye candy, making beautiful visualizations that are clear, but also compelling and also professional looking has always been a strength of the Wolfram language. We've got a little bit more filling out the space of visualizations, but also some infrastructure here. So let me show you a couple of those. Filling out the space, we've got things like 3D stream plots. So if you're working with vector fields, stream plots are basically joining up the vectors in a vector field. So you get the entire path of, say, I don't know, a particle in a magnetic field that might flow through this vector field, or a leaf dropped into a flowing river, or whatever this vector field might represent. We've had that for 2D, but now you can see we've got these lovely 3D stream plots. So there's a mixture of computation and visualization. And vector plots themselves have been extended really just in a catch-up way with other functionality. This is the bit that's new. There's no kind of new function here. But most Wolfram language visualizations work over the default, they're over the rectangle, the cuboid that they're in, but very often you want to plot things over custom regions. So imagine this is some magnetic field the magnetic flux within a physical object that is a cone, we might only want to show the visualization for those vectors within the cone. And of course, the cone isn't a special case. This can be any 3D graphics, so 3D geometry that you can construct out of all of the primitives and triangulations of real-world objects. Geographics really just wants to be like other graphics, and so it's relatively new to be able to do all kinds of beautiful maps in the Wolfram language, and we're still filling in some of the space of things that geographics should do. In this release, we've got a graph plot. So here I've got a graph, which is the connectivity of a set of cities, and I can plot that in as a geograph. So the points in the graph are placed according to where they are in the real world. Of course, any entity or geoposition will work here. Any map background, so I can do street level mapping or satellite mapping, and any geoprojection is supported. So this is the kind of the full geographics experience, but now for graphs. Most of that's about just making the correct background and putting the graph in the correct place. But there is a place where that's different, which is this graph layout option, which is new, that only makes sense within geographics, which is to take that graph network and join them up, but not by a straight line or geocurve, but by the route you would take if you drove there as quickly as possible. So here's the graph shown in driving distance. Now, another thing that is now in the infrastructure space is axis placement, and this has been a long-standing limitation that hasn't mattered for most people, but has prevented certain types of visualization. That for us, axes have always been left and right, up and down. They've been x-axis and they've been y-axis. You can put them in the middle of the plot or on the edge, but basically they only go in two directions. So now we have an arbitrary axis object that allows us to have axes in any direction. So to do this sort of ternary plot, you need three axes at 60 degrees to each other. You could fake that before, and you could do all of the hard work to place every tick programmatically yourself and every piece of text programmatically yourself. But now there's the direct axis object that just allows me to say where the axis goes and what's the range. And being typical Wolfram research, when we do finally get around to doing something, we try and do it properly. So axes don't have to be straight. Here's an axis that goes through 3 points, and they don't have to be straight. So here's an axis following a curve or a kind of parametrically defined curve. And there's all kinds of details about how many ticks and where. And in this case, I'm using tick label orientation parallel to make sure that as we go around the curve, the ticks are sensibly aligned rather than being necessarily horizontal or vertical, which are the other choices. So if you're customizing things with, example, you might want to put a scale on a geographics, those kinds of things are really easy to do now, but it's also going to open up new types of plotting within the language in future versions. Now, another one that's very much infrastructure is 3D shading. And this has always been something we've been kind of quite good at in scientific computing. In the very early days, we were one of the first to do things like lighting models for 3D graphics, so they look natural rather than these kind of horrible red, green, blue spectrum things that were shaded purely on height. And then in later versions, we've added things like texture mapping to color the surface to make it look like materials. We're now finally getting to a proper material-based shading that understands the physics of materials. So at its simplest level, we have this new function, material shading goes to copper. And here's a plot that's made to look like it might be made out of polished copper. As you'd expect, there's a whole collection of those off the shelf. So we've got somewhere, 15 odd named materials that you can just drop in. But actually, that's just the kind of ease of use tip of the pyramid of functionality, because behind the scenes, there's in fact a whole model where you can say what the base color is, what the surface normals are, how rough it is, how metallic it is. So here is a 3D scan of my face made to look like it's made out of embossed metal. And I don't know if you can really see this, but the reflections aren't, the texture of the embossing isn't just a texture. It's picking up the reflections of the light because its surface normals have been given as a texture as well. So they twinkle as if they actually stick out, even though they don't. And if you actually go through this space, there's a lot of functionality in here of how metallic it is, how rough it is, how much sheen there is, some parameters to do with the physics of materials that I have no idea what they are, but they're in there. So it's a really rich underlying rendering engine. But in the end, that means a few quick ways to flip the look of the thing, or if you can be bothered, you can make things really, really beautiful. There's a little bit on other kinds of data, not so dramatic. Data set, our quick way of rendering and working with data in hierarchical sort of key value or rectangular data sets, now supports themes. So in a single command, you say data set theme goes to minimal, and you can change the look of the thing, or marketing, and there's about a dozen of these sort of name styles that you can dress your data set very quickly without having to think through that I want the main headings to be background gray, but the contents to be light gray or whatever. You can just say dataset theme goes to name. Oh, and one very boring visualization, but missed for a long time, which is stacked data line plots. So this is a list of lists of data just stacked together. There's a never-ending list of these visualizations, and we'll continue to add them as long as people keep asking for them, and we can keep thinking of them. Right. Now let's dig a bit deeper into things that actually are kind of computational. And I think one of the biggest growth areas over the last several versions, of which there's a little bit more coming in 12.3, is optimization. That for a long time we've had functions like find a minimum and then minimize to and linear programming to be able to optimize the best values of things, operational research questions like how do I lay out my factory best? How do I set up a transport network so that I get most traffic through it, and all of these kinds of questions. What we've been building out is quadratic optimization over the last few versions to be able to do very large scale, tens of thousands of unknowns. We've been able to do that in linear programming for a long time, but in quadratic programming, that's been the domain of these sort of $10,000 optimization packages like Garobi and Mosaic. And so we're doing more to build that out. This time we've added efficient support for multi-parametric symbolic linear and quadratic programming. I'll show you an example in a moment. Exact convex optimization, and then these new support for quasi-convex and log convex. But they're all basically filling out this space of you want to know the best value. We have functionality that will scale to real industrial size problems. And we're also opening it up a bit more. So there's a framework for adding your own methods, either with a Wolfram language compiler or just by linking an external code. And as a side effect of that, we've linked it up to things like Garobi and Mosaic. So you can write your Wolfram language code when you get to the minimization step. If you want to verify the solution, or if it's still beyond the Wolfram language, then you just change method goes to Garobi, and you can farm it out. How you generated the equations can all be in the Wolfram environment, but you can still use these systems if that's what you're using now for the problem execution. Although obviously over time we want to make them redundant. Why would you go out to a separate system if it's already in the Wolfram language, better integrated and cheaper? So here's the example I promised. This is, let's walk through it a bit at a time. The idea is we've got to find the minimum value of this expression. So I've picked a pretty easy one so we can walk our way through. It's pretty easy to see the smallest value of that is going to be 0 over the reals, and that's going to be 0 over the reals because they're both squared. X and Y are independent, so the whole thing, the lowest value is going to be 0. So that's really easy to do, and Minimize has done that since the 1990s, probably 1980s. But then we've added constraints, so we can't search the whole space. We have to satisfy this constraint in X and Y, and this constraint in X and Y. We've been able to do that for quite a while for some versions. But now we're adding the constraint that those constraints are themselves parametric. There's an A and B that they depend on. Now, up to now, you could solve those for specific A's and B's, and so you could do it repeatedly, but that's kind of expensive. And when you scale this up to non-trivial problems, that expense becomes prohibitive. So now we have this totally automated way of being able to generate, in this case, a piecewise function for the minima according to different choices for A and B. And because we know how to handle these piecewise functions properly, I can take that and directly plot it. So here's the lowest possible value you can get. You can get to 0, 0 for certain choices of for certain choices of A and B, but for others, you can see the different kind of chunks of the piecewise space. But the fact that it's piecewise, the fact that it's parametric, the fact that we need efficiency, those are all just now hidden behind this already existing function min value. Now, for a long time, of course, the core has been maths. And this for 12.3 is again a mix of esoteric and practical. So there are some new mathematical functions, but they're probably only going to be directly interesting to pure mathematicians and sort of pure physicists. Fox's H is this generalized major G function, and there's this whole class of elliptic functions called Carlson functions. But the reason why these things are actually important and other infrastructure improvements is because they're behind all kinds of other functionality that you might use at the surface. So as a consequence of that and other infrastructure improvements, we've got whole new classes of differential equations that can be solved. So all of this systems of Q-rational and rational ODEs are now all solvable, whereas in many cases before, DSolve would have simply given up. And linked in with that is we've got kind of solve and reduce now handling all kinds of new bounded problems in transcendental equations, also partly thanks to improvements in infrastructure for roots. More on the ease of use sides, if you're in the PDE world, in 12.2 we added these ways of talking about partial differential equations at a much higher level. So you could talk about waves and stresses rather than having to work out what the underlying PDE was. In many ways, they were just convenience functions, but being able to talk about a wave with a reflection was much easier than saying the kind of second partial derivative of this according to some equation you've had to look up. Well, we now made it so that the symbolic differential equation solver also understands this whole language of PDE modeling component operators. So it makes it a lot easier to work at a high level, write a few lines of code instead of 30 lines of code, solve it symbolically if it can be, or switch to numerical if it can't be, without having to kind of convert it into lower level representations. Okay, I'm starting to dot through more specific domains of computation now. And geometry is an area that we've built out pretty significantly since about version 5. So for about version 7. And there's a little bit more in geometry, but it's worth saying before I actually show the things that we've done in geometry, that geometry isn't just about geometry. That you may well be solving geometric problems of how do I find the center of gravity of this object, or what's the nearest point to this shape, or am I inside a shape or not? Those kind of very geometric problems. But it's also the way we represent real-world problems to things like the differential equation solver or integrate. So when you're doing kind of real-world problems, it's very nice to be able to say, find the minimum of something given that it's inside this shape, it's bounded by this region, or find the vector field of this only within the shape of a spanner or whatever. So geometry is quite widely applicable, even if you don't think of yourself as doing geometric problems. So there's a single new function for geometric test, which provides a collection of tests and assertions. I'll show an example. And this new thing called Minkowski sum, which is region dilation and erosion in our language, and Minkowski difference. Again, I'll have to show you examples to make them make sense. And the ability to compare and canonicalize regions as well. So let me make sense of those. The region dilation is essentially the kind of furniture movers problem. If I have a triangular room and I have a round sofa, where can I put it? So the region dilation takes the triangle and moves the circle around within the triangle. So we can't cover up the very corner of the room with the round sofa, because it simply can't fit in there. If it could shrink, it could, but for a fixed size round sofa, it can't go right into the corner. So that's essentially what these transformations do. But of course, I'm picking the very simplest examples here of triangle and disk. These can be anything. This could be a weirdly shaped radio frequency footprint of a mask within the shape of a country, for example. So they could be three-dimensional shapes or even higher dimensional shapes. So this is a very general bit of functionality for transforming. I talked about kind of comparing and converting regions. One of the things that, as I said at the beginning, we're trying to make a system that joins up. Now, disk is a great symbolic primitive for a circle, or a disk in more precisely in the geometry world. And if you're doing geometry operations, it's very elegant to be able to say, in the intersection with the disk, and not have to get involved in equations or other representations. But if you're going to interact with equations within the system, then you might want the equations for a disk. Or if you're working in a logic part of the system, you might want kind of a more logical setup. So we now have a general mechanism for being able to convert between different representations. So here is the disk as a implicit region. So this is now a logic statement that if x squared and y squared is less than or equal to 1, if that's true, you're inside the region. or we can make it parametric if we want equations that allow us to trace out the region. Then here's the thing in terms of two parameters, that x and y, and the x dot and the y dot. These are the two x, y positions in terms of that x dot and y dot that map out the space. And again, that works across all kinds of primitives. And this is how we can set things up so that it's much easier to canonicalize something into a standard form and say, does this region equal that region? Are they the same? Even though they might have different representations that you created them by. The geometric test is a good example of one of these functions where it's one function, lots of functionality. This is my simplest example. I've got 3 points. So point is the kind of smallest primitive within geometry. And I'm asking a question, are they collinear? Are they all on the same straight line? And we get the answer true. And if I move one of them to a different position, we get the answer false. But it's not just a test, it's also an assertion. So I can say, actually, they are collinear, but some of the information in there is unknown, and that will allow me now to work out what's the condition I have to meet for that test to be true. So I can use this as a way of describing the constraints of a system. And here's a slightly more complicated example. I've got 2 infinite lines that have 2 unknowns in them, and my condition is that they have to be perpendicular. And here's a slightly more involved equation that comes out of that assertion. But in order to make it useful, the function has all kinds of assertions. So this is the full list from the documentation of, we can look at polygons and points to find if they're clockwise, whether lines are degenerate, whether they're perpendicular, I already showed, whether they're tangential or congruent. So there's all kinds of things that you can test for or assert in order to set up systems of equations. Okay, let's go on to a different domain before I run out of time. Graphs and networks, another big area of computational capability within the Wolfram language. There's a little bit more here again. There's some new visualization. For a while, we've had this notion of layered graph plot where, particularly things like trees, where there's a kind of hierarchy, we can lay things out so that the points are on the same level. This can get messy when things get complicated and you've got sort of potentially crisscrossing lines to be able to get them all on the same level. So to make more space to make that interpretable, we now have a 3D equivalent of the layered graph plot where we can show the relationships between the vertices of the graph, but make sure all the points that are at the same depth on the graph are in the same plane within the visualization. And with that now sort of more XY space, with the ability to rotate, you can now disambiguate and see more clearly what's going on when things get complicated. There's a couple of new embeddings. We already have a huge collection of embeddings, different ways of laying out a graph. There's no layout information for a graph, only connectivity. So I've done this grid graph, which is the simplest one I could think of. The 2 new embeddings put those points as if they're on the surface of a sphere or on the surface of a hyperbolic plane. So just new ways that for some problems will be easier to interpret the layout. Although in this case, I would say that the planar layout's probably the best one. There's a bit of new graph computation. 2 new things for vertex in and out components, and fine spanning tree applies now also not to graphs. Again, probably easier to show you what those are in practice. So here is the food chain network from one of the example networks that we have in our test data. What the in and out graphs are is effectively the influence network. So in this food chain, if I look at the mouse in graph, those are all the things that might influence the nutrition of the mouse. So it's all the things up the food chain that can lead to the mouse. So I guess if any of these things were contaminated, that would affect the mouse. Or if any one of them died out, it would have an impact on the mouse. And the mouse out graph is the opposite. It's everything that the mouse feeds into in the network. So everything it influences downstream. This only makes sense in a really directed graph because the in and out graph are the same in an undirected graph and are basically the connected graph. But this basically now allows you to very quickly pull out the entire influence network up or downstream from any particular vertex. The fine spanning tree working on things that are other than graphs now is basically about finding efficient ways to automatically construct the graph that you find the spanning tree of. So here's the kind of the toy problem, which is I've got a bunch of villages that I need to connect up with a power network. I want to find the minimum cabling required to connect every village up to the same network. So I don't care about redundancy and robustness. I just want the minimum cabling, and that's the fine spanning tree problem. Before, you could do that by enumerating every distance between every point and then finding the minimum spanning tree across the resulting graph, but that's inefficient and requires you doing work. Now we can just say for these points or geo points, find that minimum spanning tree in a direct way. And talking of trees, our support for trees up to now has been as a special case of graphs. But trees are important. There's a lot of hierarchical data structures, so things like a file system, XML and JSON are all fundamentally tree structures. And closer to home, the Wolfram language itself is always representing things as trees. So for the first time, we're adding a first-class tree object, and it comes with a whole collection of functionality for combining and editing and analyzing trees, with more to come in future versions. This is what a tree looks like. As we go down through the vertices, they split but never recombine. So if it meets that criteria, then there is a more efficient representation and more efficient computations on it. So here I'm going to take this tree and let's take the second branch of the second branch. So let's change that to 2,2. And there's the subgraph, for example. And as I said, the Wolfram language expressions themselves are graphs. So here is the expression tree. Sorry, they are trees. This is the expression tree of ax squared plus b, which we can now represent and compute on the tree itself. We've had the tree form to allow you to see this picture before, but this sort of direct conversion to an efficient tree representation is completely new, and all the computation that goes with that. Right. Right, another domain, audio and video. So we've been doing audio for quite a while. Video as a first-class object, we only added in 12.2. And so there's still lots to come with that. It's a new domain of computation for us, but this version fills in some of the things that weren't ready in time for 12.2. So there's a few convenience functions, new video generators, things like slideshow view, where I want to make a smooth video out of, say, 5 slides, but I want the video to last for 60 seconds and play music over the background or whatever. Just quick ways of being able to do those, but also quality control over those as we do them. But more significant is we have video capture now. So in 12.2, you could read videos from file, and we supported lots and lots of formats, but they had to come from file. And now we have ways to capture directly from camera, from streaming URLs across the internet, and also from your screen or the notebook itself. So if you are wanting to, you've got some application running on screen, you need to capture what's going on in that, but there's no API to reach into it. You can screen capture directly from that through your operating system. And if you're doing kind of screencast type things, you can now record your notebook keystrokes as video as you go. And there's also a whole bunch of new editing, insert, replace, time stretch, combining multiple videos. So I'm going to put together an example here, which hopefully, if I wrote this right, I was editing this just before we came on here. I'm going to do some typing into this notebook, maybe scroll the thing around and simultaneously wave at the camera as I'm going. And hopefully, here we go. It's now computing that. What I will have created now, where is it? Oh, there it is. And let's bring it across my other screen. I've captured simultaneously from the video camera and the notebook, and then used image compose to generate a video where one is inset inside the other. So I've done a sort of picture-in-picture screencast piece of code in 5 or 6 lines of code. Now, while I put that in for kind of demo purposes, the idea of composing videos as editing in the kind of movie maker way is easy to understand. It's an example that we can immediately see what's happening. Really, the value of this combine multiple videos is on the analysis side. So there are situations where what you need to do is to take 2 video sources and then compute from those. So an example might be if you have 2 viewpoints on a single scene with 2 different video cameras, you can compute geometric information about where the contents of the image is in 3D space. So in order to do that, you have to have 2 synchronized sources of video that you are simultaneously taking information from both in order to do some kind of computation. So the video map function and its friends can generate video as output, but they can also generate time series of measurements output, or they can do sort of other transformations on the content, the audio, the video, the combination of audio and video, the differences between all of these things can be done now through video map. And as we get more into that, let's make my notebook pretty again. Video is expensive. I was doing a little project for my daughter who thought that Twilight would look much better if it wasn't all filmed in moody blue and green color cast. So we tried remapping it to natural lighting color. And that's a 90-minute HD film. It takes quite a while to process through that, some hours to do that histogram mapping on every frame and making sure that they stay consistent to make this amusing video output that we created. Now in 12.3, we can simply wrap the word parallelize around that. And if I've got a quad-core computer, it'll split the video into 4 pieces and process each of them in parallel and then automatically reassemble them when it's finished. Or if I've got a kind of grid of spare machines lying around the office with permission to run on them, I could run it over 30 computers and get the whole thing done in a few minutes. And while I've not got it in this notebook, there are new ways to run parallel code using the new remote kernel object that was added in 12.2. So it's easier to fire up remote Wolfram language or Mathematicas on other machines that you have SSH type access to. And another thing on the integration, trying to make this unified computation, is that we are always trying to add the hooks into machine learning as we go. So there is now a basic video encoder for the neural network framework that allows me to use video directly for training purposes, or really for training purposes, or for execution purposes. So at the moment, that is single frame at a time video encoder. A time-based video encoder will come later, but already we have that ability now to just do net train of video and do sort of supervised learning on video sources. Now that leads me into machine learning. Again, a big exciting area for us for some years now, and we have a really high level and powerful machine learning framework for either doing fully automated machine learning or if you're more expert, building custom neural network architectures. So we've got a couple of things that are more at that automated end. 2 things that are really about explainability. I'll show the example of Shapley-based feature explanation, but it answers the question of why when you do machine learning. And we also added control over calibration. So when you do classify and predict at the moment, what they give you is a percentage. If you ask it for the percentage, it says, oh, this is 50%, 90%, when it makes its probability prediction. It's a bit subtle, but what that really is a confidence measure of the predictor. So if I don't give it very much data, if I give it 2 examples, typically it gives me 100% when it makes its prediction, because if it matches one of the data points, that's all it knows about the world. It's got no doubts. It's an overconfident fool that doesn't understand its own limitations. What we can do now is during the testing phase of neural networks, you can ask it at the point where you're measuring how successful the predictor is to align that success to its own levels of confidence. So you can recalibrate that confidence to say, well, when you said you were 90% accurate, actually you were underestimating your abilities. Whenever it was 90% accurate, you were always right. That's 100%. But when you said you were 70% accurate, actually you were being overconfident there that it was only right half the time. So you can then start asking the predict and classify to give you the probability that you get the right answer when you make your prediction or classification. There's some details related to that of how you synthesize missing values, more things for the kind of more expert neural net builders, some new layers, and the ability to tie in with feature extractor, which is one of the main unsupervised learning mechanisms that we have. You can now join together with the net encode as a way of passing things into a neural network, so you can mix unsupervised and supervised learning more easily, and then some improvements to some of the infrastructure that goes around it. Let me show you this Shapley example, because that only really makes sense when I show it. Here I'm going to do a quick bit of machine learning. Let's get it running. I've got a data set coming from the Wolfram research data repository, the wine quality sample data set, and I'm telling it to predict based on I'm wanting to predict the wine quality measurement out of that data set. And I'm giving it a wine I'm not sure if I'm cheating here and it's seen this example, but hopefully an unseen example. It actually had a wine quality of 8. My predictor's done so-so, it's made it 7. I think the scale is 1 to 9. So basically it has spotted this looks like a good wine. It's not quite got it right. But the question is, why is it a good wine? And as people get kind of concerned about things like bias, they think that explainability is a useful criteria. So this new property of the classifier, the predictor in this case, is SHAP values, allows me to quantify where that prediction came from. So the plus numbers here mean that they contributed to the decision that it was a good wine, and the negative numbers actually argued that it was a poor wine. So it actually had the acidity qualities of a slightly poor wine. And if we look for the biggest number, we can see that top of the list is it's got a spot on alcohol content. So we're not saying whether high or low alcohol is a good thing, but we're saying that that's the thing that's most influences the prediction that this was a good wine. So being at about 12.8 is probably a good thing. Maybe it's higher is better, or maybe 12.8 is the sweet spot, but that's it's added 0.35 to the score for that feature alone. And then the next biggest is, I guess, the free sulfur dioxide, which has added 0.27. So between those, they've added half a point to the prediction on this 10-point score. And that works also for predictions as well, using the predict function. Sorry, the classify function. Okay, this seems a bit boring, but as somebody who works at the coalface of data science a lot, parsing dates in different formats is a real pain when you get a big data set and you've got a column of dates, and the dates come from some weird system or from some weird place, and you end up having to write custom code to say, split it on this character and take this bit to mean that, and so on. So we've got a new framework for parsing dates that is linked into language and locales. There's a bit more on daylight saving, which is kind of a detail that we just need to get right, that between me and the US office of Wolfram Research, there's a 6-hour time difference, but not for slightly under a week a year when daylight saving changes on a different day in the US. And for an hour during the change, it's different as well. So being able to get that right is just one of those details that we're always trying to pick up. And if you are in the astronomy, astrophysics world, then there's some things to do with measuring time in ways other than the atomic clock, about where we are in terms of the sun and the universe. But let me show you the date parsing. I'm going to start with something that, as a European, has driven me mad for a long time, that it wasn't easier to do, is parsing a date like this. Now, Wolfram language always parsed date like that, but being a slightly American-centric view on the world, that in American convention is the 2nd of January. But to most Europeans, we work in ascending order of size, so that's the 1st of February. And now I can tell it that we're in British English, and from that, it's figured out it is the 1st of February, not the 2nd of January. So it's taken the British convention for date parsing. And in future, it'll automatically figure out from your machine which place you are in the world. Now well, that one personally drives me mad up to now. Actually, the problem is much more complex than that. So we have bidirectional parsing in a whole bunch of formats. So now, for example, I can make that date string in Japanese, but more importantly, if I've got the date in Japanese, I can figure out what that date is by reading back the Japanese string. And there's lots of detail controls to say, well, actually, I know it's Japanese, but I know actually it's only month and day, it's not year. And so you can roll up your sleeves and take more control, but we're trying to make these things automatic across what turns out to be quite a large number of languages. Has been a reasonable chore to get right. So now there's all of these different conventions for translating to and from dates that are essentially automatically supported. I just noticed Welsh is on there. I hadn't noticed that before. So yeah, some of the major languages, some of them fairly minor. Right, let's go into more specific domains now. Molecule is a slowly emerging area for us where we are trying to make computational chemistry just as easy as computational maths or computational engineering. And there's a few more things here which are to do with handling of molecules, so we can name them, and we can also do alignment and structure analysis better than before. So here's a typical thing in the molecule framework. I've given the, I forget what the SMILES representation of a molecule, and now we can look that up and say, well, can you figure out what the name of that molecule is? And it can do a pattern matching and say this is this 1,2-dichloroprurine. And of course, that fits in with other things in our system. So I might even have the thing in as a picture from a textbook or from an academic paper. I can pass that through molecule recognize and into the molecule name to figure out what that thing is from its picture. And the molecule alignment is about taking these kind of molecules. I've got 2 extra here, plus the one we just imported, and look for what they have in common. And we can find the pattern, this sort of substructure within the molecule now that has been identified, and we can display that to see here's the substructure on the 3 molecules. So we're actually adding these abilities to start doing sort of computational steps on these things rather than simply representing them. And again, in terms of integration, there is now a classifier encoder for molecule. So we can now do machine learning on molecules as well. You can say, here's a whole bunch of molecules that are acids, here's a bunch that are alkali, here's one you've never seen before, can you guess whether it's an acid or alkali? And it'll figure out from the patterns of the molecules which it's most similar to. And obviously you can imagine much more interesting questions to ask than that, which I guess is pretty deterministic. Okay, we're now getting into the kind of space of boring but important is connectivity. We're trying to make it not just Wolfram language a kind of exploration environment for analysts and scientists and engineers, but something that you can build real systems out of. So connectivity is obviously always important for that. We got some new things in that space. To me, the most interesting was this external storage object that we have that supports Dropbox and IPFS at the moment. It now supports an important one, which is for professional use, which is Amazon S3 buckets. So you can read and write data directly into the Amazon storage. So if you have terabytes of data, you can rent the space in Amazon to store that. And now we can reach into that and fetch out the piece that needs analyzing, do analysis, push the results back into the S3 bucket, as long as you've set up your credentials into the Wolfram language system. There's a whole bunch of cryptocurrency and blockchain and cryptography support. To me, the headline one, if you're not a blockchain or crypto fanatic, is OAuth 2.0. So you need this if you're going to connect into external services. This is the more modern version of OAuth, and this is about how you make one web server or application prove itself to another so it can log in automatically over remote services. Within our own ecosystem, we've got improved support for working with System Modeler. So this is the application for large-scale system simulations where you're modeling the entire performance of a car as a kind of digital clone of the car. Well, now we have the ability to generate simulation data within the Wolfram language and drop that straight into the Modelica system modeler world. And we can work directly with system models you've created in the system modeler world and compute with those for things like control engineering problems directly within the Wolfram language. So really just about making it more seamless join up with the rest of our ecosystem. And there's a little bit more on data. We have one new format, the SAS data format, but a whole bunch of the other data formats have been improved. So most of the video formats have new properties that you can import and export to. Likewise, there's new properties and improvements in some of the image formats and a few of the data formats, but only one that's completely new this time. But I guess that still means that it takes our total up a little bit higher to a total 235 different formats that we support now with that extra one. So I pretty much hit the hour that I was aiming for by going very fast. It's been a whirlwind tour of some of the functionality. To recap, before I try and take questions, the questions will reach me, although they will take a few seconds if you put them into the chat of whichever platform you're viewing through. Really, the overall summary is that it's an everything release. There's performance improvements and infrastructure improvements and notebook improvements right throughout the system. And bits of functionality in a whole bunch of the different domains. So we've got the maths, the optimization, video, geo, vector, and I'm missing a couple that I went through: machine learning, significant improvements, optimization. A lot of these different domains that also sit behind other things within the system. Optimization is called on by all kinds of other functions just to make the algorithms work. These infrastructure things will permeate out beyond just the functions that they are kind of obviously a part of. And a little bit on the data science of data import and export as well, being more convenient. So thank you very much for listening, and and I would love to take some questions. And I'm just waiting for any at the moment. There's a comment from somebody who's testing, who's asking about front-end regressions. The final version was approved, I think it was about 3 days ago for the desktop deployments. So we should see that ship within the next few days now. I don't have a definite day, so watch our space to see that. But yeah, things were, a lot of the kind of late bug fixing was cleaned up in those closing weeks after we finally sort of feature froze everything and went into full-time bug fixing. So you'd have to say which one you were concerned about for me to confirm that it's definitely closed out. But I know that that a bunch of things that that I was seeing were closed out all in the last couple of weeks as we focused on quality. And for those of you who are interested, while we have not shipped this on the desktop yet, you can already, because some of our infrastructure takes time to update, you can, let's get a browser running here. You can see the documentation already in reference.wolfram.com, because that takes a while to copy up. If you go to reference.wolfram.com and click down on the new features at the bottom, that is already up to date now with the 12.3 feature list and documentation. And if you're Wolfram Cloud users, some of the Wolfram Cloud nodes are already up to date with 12.3. Again, they take time, so you might get a 12.2 node or 12.3 when you log into the Wolfram Cloud, but they are being upgraded as we speak. So really the only thing we're waiting for now is the desktop releases as we get ready for those, and in a few days whenever we do release, you'll be able to see a kind of much more of the story behind, and probably much longer screencast Stephen Wolfram will be doing to talk about the story behind some of the design of these things, and how we've gone about them, and will have his own personal view on what's important and what isn't. And those of you obviously with Premier Service or on site licenses should be all able to receive your downloads within a few days at the most. Do student accounts of Mathematica get those improvements? Yes, we have ever since before I joined the company back in 1992, we have always had the attitude that students don't do kind of dumbed down educational things, they solve real problems too. So the student version of Wolfram Language is full functionality. The only limitation is a licensing one, that you have to be a student to be eligible to use it. Okay, question, what's your favorite thing in 12.3? Any hints on version 13? Okay, let's take the first question. Personally, I really like the Shapley values that give explainability to machine learning. I'm quite a heavy notebook user, so I have been using the code checker for a while now, and that's really been a quality of life improvement for me, because I'm a very careless typist, and trying to figure out why code doesn't run because you missed out a comma or put the wrong bracket somewhere. Oh, actually, another thing which I forgot to show, which seems like an important one for just minor life benefits, is that if you now type brackets, you have to enable this, it's off by default, but when you type into the system now, as you type brackets, they auto close for you if you like that, and I really like that style. As I type the curly bracket, it auto closes. As I type the association bracket, it auto closes and leaves the cursor inside, so that I don't have to constantly be forward typing and backwards typing. And also even things like the double square brackets now for the first time auto complete into a double bracket notation. But even more importantly, if you've got that wrong, when you hit backspace, they go back to being what you had before you typed it. It's holding the actual keystrokes, not just the character it's become. So things like the arrow auto conversion, now as you back type, the arrow doesn't delete in one go, you get the minus sign back. So if you want to actually meant to type something else, then you've not lost your keystroke. So that's a really nice minor feature. And hints on version 13, I daren't go there. I see the roadmap for lots of things that are coming, but we never quite know until relatively late in the cycle which ones will have converged well enough to make the cut for the next release and which ones will be punted to future versions. I've made that mistake before, saying, oh yes, in the next version you'll get this, and then it doesn't arrive for 2 more versions because it turned into something grander, or it turned out to be harder than people thought. But some of the things I've shown today will all continue to develop further. There'll be more chemistry, more on the question framework, more on the form functionality, Machine learning is not stopping in its version. So all of these areas under active development, you can pretty much predict there will be more of as we go into future versions. So comment code checking looks really good, and direct access to the shell is also great. This direct access I've actually found very useful more for things like data, that I do stuff sometimes with local databases. So to be able to type a notebook and do SQL and do things like select star from users on a database that I'm working on, and have that in a data set that I can compute with locally, I find really useful. So if you are using things like shell, I can imagine you get the same benefits from having those within Wolfram language. For me, the SQL version of it was the big improvement back in 12.2. Any chance of Voronoi 3D? When do we get it? Now, give me a moment here. I had thought that Voronoi Mesh in 3D was updated in 12.2. Yes. Now, either I'm misremembering that, or it was one of those things that was going to be in 12.2 and got bumped at the last minute and still hasn't made the release. So we'll have to follow up that question afterwards. If you make sure we have your email address, then we'll get you an answer on that one, because it's clearly not there at the moment. Can we form Laplace transform in Mathematica? There is there is Laplace transform already in Mathematica. One of the things I slightly skipped over to keep the pace going in the math section is we now have in 12.3 maths, here we go, under calculus, there is now support for bilateral and double-sided Laplace transform. So the standard Laplace transform is sort of 0 to infinity, sort of future time things, and the double-sided allows you to do the integrals from -infinity to infinity. Any upgrade on Eclipse integration? Yes, so the answer is no on that, really. There's not really a huge amount of work has gone into that recently, keeping up to date, and I would certainly like to see more on that. I have to say, from a personal point of view, I recently switched to IntelliJ, which has a third-party plugin which costs, I can't remember what I paid for it, £10 or £15 or something. So $20 for the Wolfram language plugin, and that's really good. I prefer IntelliJ to Eclipse. It just all seems a bit faster and better designed, and the plugin that's been developed by this third-party developer is a really nice plugin as well. And the code profiler, the code inspector in that is automatically attached to git commit. So the moment you commit, you automatically get a warning saying, "Are you sure you want to commit? There seems to be a missing comma," which I found a real lifesaver. So I can definitely recommend that as an alternative to Eclipse. Yeah, Wolfram Workbench is still, it's still not something. I don't want to be too down on it. It hasn't received the attention it deserves, but it is not something that we're planning to discontinue. It's getting kind of minimal updates at the moment, and certainly I've been lobbying to try and get it up to the same standard as the IntelliJ plugin, and making use of some of these newer features. There's plenty of people inside the company who use it, so that helps to drive the fact that it's important to us. Improvements to the GUI. Well, I mean, the notebooks things that I showed at the beginning are definitely things that I would consider as things that affect everyone that are GUI improvements. They're fairly minor things, but if you're writing code all the time, things like code analysis and delimiter matching really kind of are improvements to one's lifestyle. We're not big on creating kind of big point and click interfaces. Our kind of principle is language first. But some of those things that we're using to make interfaces, we've been exposing incrementally for you to be able to make custom user interfaces. All of these things like attached cells that were added in 12.2 that are what we use. If I, for a while we've had, when you click on an image, you get these kind of interfaces that pop up underneath. We added a bunch more of those in 12.2, but I think more importantly, we exposed the technology by which we make these, so you can create your own types of attached cell interfaces, and whether they go away when you click out of them or and so on. So that's really our main focus on user interfaces, is kind of equipping the infrastructure. So where can I see examples of problem solving in quantum mechanics using Mathematica? So there was going to be a whole bunch of quantum mechanics functionality in the Wolfram language. In the end, the decision was made to push it into the function repository. So if you go to, let's get the browser back up again, Wolfram function repository. Let's just get that open here. Then a lot of that functioning has already been landing bit by bit within this. So these functions all work directly in the Wolfram language without you having to do anything. So I don't have a quantum physics background, so I have no idea what these things do. But so quantum discrete state of what looks like a complex number and a value, I can click on that, go back to my Wolfram language, paste that in and compute. And the first time I do it, you'll say finding resource, and it's now just added that functionality into my Wolfram language, so a kind of a package repository mechanism. And I've got this quantum discrete state object back, which presumably is usable in other functions within this collection. So I would suggest you take a look there for the quantum functionality. There's quite a bit, but I can't tell you whether it's any good or not, because I don't understand quantum mechanics at all, to be honest. Right, have I missed over any questions here? Because there's a whole bunch on my screen now. So somebody said, so you get different results on different machines. That's a reference to the embed, the save the reference in the document. So that actually, that embedded data hookup to a local object, it's generating a UID. So if I do a local storage and I send that notebook to a different machine, it simply will say not found, and it'll be the same as if I hadn't done anything. If I put it into a cloud storage, then it will be able to access the shared data regardless of which machine, if I click the button to say store in cloud. Although if I want other people to be able to use the notebook, I'm going to have to go and separately change the permissions on that cloud object to make it public. Otherwise, you'll get a permissions failure when you use the notebook from somebody else. But you're not going to get the same notebook picking up different versions of the data depending on which machine you run it on, because they will always be unique. The worst case is it'll be a not found error or a not permissioned error. And obviously there are things that are non-deterministic in Wolfram language, but that's a kind of separate problem, I think, than you're asking about. Oh yeah, somebody else saying the plugin for IntelliJ is really useful. Right, we seem to, I think I've answered all the questions that have come in so far. I can't see any that I haven't. So you've got a few seconds left to get one to me, or we'll wrap up. And I would suggest that you pay attention to our Twitter or news feeds. And for that matter, if I put back on screen my own here, feel free to watch mine. And as soon as we have the desktop release and the timing for Stephen Wolfram's version of What's New, we'll post that out, and you'll be able to get your hands on your own copy. But it is in the space of days, if not hours at this point, not weeks. Well, thank you very much, everyone, and I will stop there and wish you all the best of luck in your computing endeavors. Bye-bye.